Well, good morning. Thank you for joining, and thank you particularly to the Irish chapter of the IAH for organising today's meeting. My name is Dan Lapworth, and I'm here to kick off the day and to introduce a little bit of background to R for hydrogeology and show you some examples. This is not a formal training course in R, it's really just to show you some working examples, things that have been useful for me and others in learning R and applying R within our work. So a brief overview of the next 40 minutes. I'll be covering a little about the origins of R and where it is today. I'll be communicating some key concepts of R, trying to give you some reasons why using R is good and trying to demonstrate that. I'll share a brief overview of my R story, so how I got into R and how I've used R throughout the years. I'll show you some examples where I found R to be particularly helpful in undertaking tasks. I'll try and avoid where I can showing any code. I'll show an example at the very end. And then there'll be a bit of time left at the end for some coffee, a bit of a breakout, and some questions and answers afterwards. So to start with, R, what are the origins of R? Where did it come from, and what's its progress been so far? So R was originally a programming language called S that was developed by a statistician and programmer called John Chambers, based at the Bell Laboratories in the US. And this was in the mid 1970s. Now, the S language was implemented within the R programming language by two academics at the University of Auckland, Ross and Robert, and that's where the term R comes from. So this was started in 2000 as a formal programming language which implemented S and developed S further within the R program. The core development team for R has coordinated the ongoing development of R over the subsequent years till today. And the basis and principles of R were that it was open source, copyleft, and free for users to use. Today, it's the ninth most popular programming language overall this year. And today there are many packages that people can use within R. I think there's over 18,000 different packages to undertake different tasks. So it's a huge, diverse programming language with a number of tools that are very useful for different groups. R is arguably a first choice program for statistical analysis. But there are other programs, and its main competitor, arguably, is Python. But this is often seen as a bit more of a generic programming language for handling data sets and undertaking tasks. But there are many common features, so it is a genuine competitor. The graph you can see down in the right-hand corner is just a time series showing how the number of packages have developed within R over the years between 1998, when it was being developed, through 2006, and how that's continues to rise almost exponentially. So some of the basic concepts of R. So R is a command line programming language, typically used these days in combination with an integrated development environment, so such as RStudio, to help tag up the program, the language and the text that you put into the programming environment. But that wasn't always the case. It started off as a command line program just in the console itself. Data analysis with R is done basically in a series of steps, logical steps, sort of programming, transforming data, discovering data, analyzing data, and then finally communicating the results from that analysis. And it can handle all aspects of those different steps within the process. A series of packages and embedded functions are used to undertake specific tasks within R. And in some cases, a group of packages, for example, in the package tidyverse, these are linked together to provide a collection of functions to do all these steps within one sort of environment. And you'll hear more about that from a talk later today by Donald John. So some of the basic concepts to start with. One important feature is that it's interoperable with many other platforms. So you can use R to drive, move data around, and have access to other platforms. So it's very good at connecting with other platforms, be it Python, be it other programming languages, other databases. It can be effectively used to link to databases, websites, and other data analysis tools. And there are lots of packages within R that do similar things, so that's good to be aware of that. There are many options when you want to do particular tasks within R, so you're not just forced down one particular route. The comprehensive R archive network, known as CRAN, is the archive where all the packages and the documentation and the program can be downloaded from. And this is a particularly well documented archive and very helpful for getting going. It's been heavily validated as a programming language, and this is because of the large user base it has, and it is probably the most scrutinized stats software in the world. So in that sense, it's gone through a lot of checks, it's gone through a lot of validation. It's a robust statistical tool, and it produces really high quality graphics at the end of the day. There's an example at the bottom there which shows a violin plot, which is like a box plot, but also shows the distribution of data, which can be done in one line of code. So it's a very versatile tool, and it can be used to produce very high quality graphics. But you have a lot of choice. You know, you're not just forced down one particular route. There are lots of ways of analyzing the data and producing graphics within the R environment. So why use R? Well, it's definitely, arguably, the best stats package available to us. So that's one reason. Secondly, it produces excellent quality graphics, publication quality graphics. So that's another very strong reason for using it. And probably most importantly, it has a huge selection of tailored packages with very good documentation to help you through the process of using it and putting your data together and actually producing the graphics or analysis that you want. There are a number of other reasons. It can handle and analyze data from input through to communication. So it provides that holistic package in that sense. You can do repetitive tasks very easily. You can organize data, you can do statistics and do plotting, all in a very systematic way, and in a way where the workflow is quite efficient. And therefore it saves time ultimately. However, it does take a while to invest in learning the package early on. It's open source, that's another great reason, and is very interoperable with other platforms. But it's fair to say that R is not the only program for doing many of the tasks. So look around when you're thinking of doing something. You know, there may be another package, there may be another program that will be more suitable. There may be another big tanker that's coming over the horizon. So getting started with R. Well, first of all, it's very good to remember that when starting with R, it is a very steep learning curve, as it is with a lot of programming language. There's a lot to learn early on, and you don't always make as much progress early on. So bear that in mind. There are many great online courses and tutorials available to starters, and a couple of these that are used by lots of people today are Data Camp and Code Academy. So I'd certainly encourage you to look at those if you want to get started. The web, of course, has lots of brilliant examples and help in terms of code development, and there are YouTube clips. So there's a lot of help out there on the web through Google searches, etc., to try and help debug the code you're putting together and learn about it. I think it's important, it certainly was for me, to try and find an R buddy, so somebody who is more familiar with R, who can help you earlier on and get you going. A top tip, you know, when you're trying to do some analysis in R and a series of tasks, try and break it down into simple, discrete steps, and that will help simplify the problem for you, rather than trying to do it all at once. And of course, there are lots of forums these days, and you'll hear a little bit about those from others. And there are many experts out there, so you know that there's a lot of resources and a lot of people out there that can help you when you're actually in the process of putting some code together. And of course, there are lots of traditional R books and materials with really good work examples too. So there's a lot of help out there. There's a lot of stuff to get you going and to help you along the way early on. So in brief, my own story of using R, sort of a quick run through of how I got into it and how I found it. So when I started using R, it was back in the early 2000s. So it was just console based at that time. And I started with an enormous amount of initial enthusiasm. I had two colleagues at BGS, Dave Kinneborough, who was particularly enthusiastic about the programming language, and another colleague, Chris Milne, and they kind of got me into using and starting to use R. So I started with a lot of initial enthusiasm. However, there were some fairly obvious early frustrations. You know, I wasn't a coder. Didn't have a lot of background or experience in using code or writing code. So it was, to be honest, it was fairly hard work for me, and I needed help early on. And I'm thankful for Dave and Chris for helping me, and also some of the online forums that were available at the time. But within a reasonably short period of time, there was certainly payback for that investment, and I was able to use it as part of my work. And it opened up lots of possibilities in terms of data processing and analysis. And I've continued, you know, over the last 15 years to learn and develop my skills in R, and in particularly encouraging others around me in the workplace and colleagues to try and get started where it's suitable to use R. So it's certainly been a journey a bit like that picture down in the bottom right hand corner, where I started with a fairly steep climb, learning curve, but eventually I reached the plateau, and I had my payback time in terms of it being really useful for me in undertaking tasks at work. So it was worth it. So here are some examples, some old, some new, some going back many years, and some more recent, where R has made a really big difference to me in my work, helped me out in particular incidences to undertake tasks efficiently, and helped me sort of analysing small and large data sets. So I'll run through a few examples in the next few slides to show you these. So my first example, which was pretty much one of my first experiences in R and first applications of using R, was to look at quality control data within the BGS groundwater laboratories at the time. And a key part of quality control within laboratory analysis is to track how known standards perform during that analysis. You know, are they providing reproducible data and consistent data and correct data, or are things drifting? And ideally, we need a quick way to visualize results and compare the performance of these standards. So the solution for this, for us as a laboratory, I was working half of my time in the laboratory at that time as a geochemist, was to use a dynamic Schuhart plot. So this is a plot which shows how a particular analyte for a standard is varying with time, and if it's within the control limits, the upper or lower, within that boundary of the upper and lower control limits, or whether it's deviating from that, and therefore we need to investigate and redo the analysis to get some robust data. And this is exactly the sort of thing that's used around the world for producing goods, for example, Guinness, to make sure that there's consistency in taste, aesthetics, smell, etc., etc. And it's exactly the same thing that's done within the food industry. So how do we go about it? Well, we developed a program in R to effectively import new data from the instrument as it was being produced and put that together and compare that with the historical data for that same standard. We embedded a prompt in an Access database to actually call on an R routine. This sort of demonstrates its interoperability. And there was a practical requirement. This was a tool we needed to develop and to be used by all the lab staff, so not people who are programming in R. This worked quite effectively, and I'll sort of show the workflow below. But overall, it certainly made a great difference in terms of our ability to check the quality control results that are coming off standards from our instruments and cut down our time needed for checking considerably, probably between 50 and 90% in many cases. So we had, to show the process at the bottom here, so to start with, we've got our data sets, our historical data set in an Access database. We select a quality control standard and element of interest, and then we press go. Now within R, we import data from the Access database. We import the new data off the instrument, and we select the new data and analyte that we want. We then calculate these upper and lower confidence limits and the confidence limit and the standard value itself, the CL value, and we effectively plot these up together, as you can see in that plot on the right-hand side. And we're able to show the consistency of the analysis, and also able to flag up and plot clearly violations that are sort of drifting either above that upper control limit or below that lower control limit. And in that way, quickly check whether our day's analysis has been okay, and we can import that into the database and use it and report the results, or whether we need to investigate further. And there are a couple of functions we used early on, very simple functions that are used by lots of people, the plot and the point functions within R, to sort of construct these graphs and flag up the violations. So my second example was a bit further on, a few years later, and I was involved in a large geochemical mapping project in Madagascar to look at the stream sediment geochemistry of Madagascar. So this was mapping a very large area, 240 kilometers squared area within Madagascar. That's roughly 12 times Wales. That's the kind of universal measure of size. So a big area, and a huge number of stream sediment samples we were collecting across this area. So it was a massive, massive fieldwork challenge, but also towards the end of the project, we had to produce geochemical summaries and statistics and produce maps of this area. So that's particularly where R came in. So the challenge was towards the end of the project. We had about 6 months of time left on the project, and we needed to QA all the geochemistry data from the stream sediments and produce statistics for those, and also produce 20 sheet maps that show the distribution. And this called for a very rigorous and automated workflow. And a large part of this ended up being done in R. So I constructed an Access database to start with, to host all the data. This was quite a large matrix, sort of 14,000 rows and 52 different columns, so nearly 1 million results within the database. And within the R environment, I used R to QA the data, as we've seen before, check how standards that we had inserted were performing, how reproducible rep samples were, etc. I used R to calculate summary statistics for each map sheet that we needed to report. And as well as that, I needed to account for results that were below detection limits and use robust statistical methods to look at summary statistics. And as well as that, produce plots and maps and plots that would go within the maps themselves. Now we ended up using ArcGIS to produce the final map sheets, but equally we could have, and I would do today, we could have produced the map sheets within the R environment itself. And there are a number of packages that I use. both to process the data, quality control it, but also do the various plots and analysis. So that the NADA package to look at calculating robust summary statistics, even though we have a lot of sensor data in there, using the sense box plot function, histogram and box plot functions, and cumulative probability plots, which were used on the maps. So the third panel just shows a few examples of more classical hydrochemistry plots that I've used to produce sort of publication quality plots. So on the left is your classic Piper plot, which shows the type of water in terms of its hydrochemistry, and how that relates to the salinity. So the larger the point within that ternary plot, the higher the salinity. So you can produce some of these fairly classical hydrochemistry plots within R. Box plot functions I use very often, and I've used this in the past. This particular example just shows the distribution of a groundwater tracer, a residence time tracer that we use in hydrogeology, CFC12, and how that varied within the shallow groundwater system, the S box plots, and within the deep groundwater system, the darker blues there, so pre and post monsoon, and how that varied. And then below that, estimated mean residence times and how they varied for the samples. On the right-hand side is a sort of an XY plot, really, with a number of different regression lines, and this is typically used to analyze and interpret stable isotope data from groundwaters and understand recharge processes. So there are a number of classical plots that you can do quite simply within R using those functions that I've mentioned there, sort of Piper dot diagram, box plot, and the plot function. So my fourth example is a more recent example where we were contracted by the Environment Agency to analyse and produce some maps of groundwater contaminants, or organic contaminants in groundwater within England. So this was a project commissioned by the Environment Agency, and the main challenge for this project was dealing with a large proportion of below detection limit results. So for that we used, again, I drew on my experience with NADA to sort of calculate robust summary statistics, and then used the censored box plot package within that to plot up the data and look at distributions of the data. And then secondly, a colleague of mine, Andy Mackenzie, and Emily Crane used the leaflet and shiny programs within R. So these are sort of for producing interactive maps, particularly good for websites, of course, to actually start to map and plot out the distribution of some of these organics. And this code that we developed and the workflow that we developed as part of this project is now actually used by the Environment Agency to process and visualize their own data themselves. It was quite nice to see that taken up and used within another organisation. The fifth example was some work we did looking at groundwater quality in Africa more recently. So this was data from a large number of hand pump boreholes in Africa, in Uganda, Malawi, and Ethiopia, from about 400 sites across these countries. And I used R to analyse the water quality data from these sites using a range of methods, using box plots, as you can see on the diagrams on the right-hand side, to test particular hypotheses that we're exploring, and to assess correlations, for example, between different parameters. And I was also able to use our simple functions in R to arrange the plots, multi-panel plots, which is often quite useful for publications where you've got limited space, or you want to show a lot of information at the same time. So the types of packages I used were sense box plots, again, the plot and point functions, which are very simple, the core test function for looking at correlations, the AB line, which is a simple function to add horizontal or vertical lines to plots, in this case to sort of show the WHO limit for the various parameters that exceeded drinking water quality standards, and the PAR and MF col functions for controlling the plot layout, so the number of rows and the number of columns and the number of individual plots within that kind of matrix. So I was able to quite quickly produce this fairly complicated plot within a few lines of code, and combine, you know, box plots and dot plots and correlations all within the same plot area, and annotate it and label it. Yeah, a relatively easy way to show a lot of information quite quickly for using multi-panel plots. Now, my next example also uses multi-panel plots, but this uses a particular package in R called Lattice. And in this case, I use the XY plot function to look at groundwater level time series for North India, for Bihar in particular. And I was exploring the changes in groundwater levels from 10 different sites across a catchment that we'd done some research on, to see if there are any sort of medium-term trends in groundwater levels from the monitoring data. So this particular plot I put together in one line of code after processing the date information properly, which was needed in R and needed for this particular function. So this particular plot, I used the XY plot function in Lattice, but also showed the dates as points. I joined lines between the points, and then I also did a regression on the time series to see if there are any particular trends at sites. So this is the only example where I've shown a little bit of code, R code, just to give you a flavour for what it's like if you've not seen it before. So at the bottom, the two lines at the bottom are what produces this particular plot. So I call on the XY plot function, and then I'm saying plot water level by date for individual IDs, so for individual boreholes within the data set D, data equals D. And then I'm saying within this plot function, I'm saying XY plot function, I'm saying, well, please plot the points P, the lines L, and what's termed smooth, which is this lowest regression smooth plot, which is also an additional line that you can see running through the data. And then the rest of the code is really related to labels, so x-axis labels, y-axis labels. So you can see I've added a y-axis label, depth below groundwater level, controlling the x and y-axis sizes, so they're consistent between the plots for comparative purposes, and setting out the plot as I described before, so the spacing between the plots, etc. And this as you can see, generates quite a nice time series of these data points very efficiently and very effectively. So you can see how it would be very useful for looking at monitoring data from loggers as part of studies that you're undertaking in a very kind of quick and efficient way. So the key messages from the talk this morning, I think overall the thing to remember, you know, and take home is R has a lot to offer the hydrogeology community. You know, there are many different packages, many different applications and functions that you can use within R, and often a good choice within R in terms of how you do that. It may be particularly hard early on, and I found that myself, but I certainly found that it was very well worthwhile investment in my time early on, and it certainly has paid back hugely through helping me as a hydrogeologist to analyse data and undertake my research. So it's definitely more than paid back many more times the time that I originally invested. And I think it's good to remember as well, you know, I wasn't a programmer, I wasn't particularly familiar at all with programming when I got started. So you don't have to be a kind of a programmer type to use R. It will certainly help, and and it'll take you a bit longer if you aren't familiar with programming. But you don't have to be a programmer to get on with R if you put a bit of time and effort in. But equally, you know, it's fair to say R is not for everybody. So it may be that there are certain people within your organisations that have those kind of aptitudes and skills and can take it on quite quickly. Others may get frustrated if they don't make much progress and they find it difficult. So as we get to the end, I draw to the end of my talk, I thought I'd leave you with a few particularly useful links. So the CRAN website where the archive is of R, and you can download the package itself. There is a website for the R project, so that gives you a lot of sort of news updates for R, and as well as the R journal and various other resources, online resources. It's quite a nice R graph gallery, which I think is good as well for kind of giving you a bit of inspiration for the types of plots and types of things that you can do in R, and the ways that you can analyze and plot up your own data. And I'm just mentioning again this online resource, the Data Camp site, which has a lot of kind of free tutorials, particularly when you're getting into R early on, introductions to R, and some of the R analysis and some of the packages that are frequently used by people. So that's a really good resource as well to highlight. So thank you for listening. I hope it's been helpful. I hope it's been a good kind of overview and introduction to R, and shown you some examples of where it's really been effective in improving my ability to analyze a lot of data very quickly and improve that workflow within the tasks I've undertaken. I think there'll be a bit of time now to sort of break out and have a coffee. And then after that, there'll be a Q&A session to follow if you have any questions. And I thought I'd take this opportunity just to highlight and bring to your attention the new IH Groundwater Quality Commission, which I'm chairing, which got going recently, and just to encourage you, if you're interested in groundwater quality, please have a look, please join and have a look at some of the initiatives we're currently developing together. Okay, well, thank you for your time, thank you for listening, and I'll be with you in a few minutes for the Q&A. Thanks a lot. Bye.